Right. Again, Assalamualaikum warahmatullahi wabarakatuh. I'm going to show you now. We've talked about adaptive control, and I've shown you a little bit about stability. The objective of our adaptive control just now is to ensure stability of the system. But maybe some of you wonder, what does it mean by stability? So when we have a system, I just give a brief description of what do we mean by a stable system, okay? A stable system is when you apply an input to the system. Let's say I apply a standard step input or a standard impulse input, okay, or I apply a standard sinusoidal input. All right. So when I apply this type of input to a system, okay, and then I check the response of the system. If it's a step input, maybe if the response of the system, this is the input that I want, okay, the reference that I want, but maybe the system is responding this way. All right, it will actually maybe increase a little bit, and then maybe it's settled down there. Then the system is said to be stable. Why? Because the response does not increase with time. Okay, the response will actually either it is settled at certain value or it reduce. Okay, sometimes the response can also goes up like that, and then suddenly it will reduce. This is still stable as long as it's reduced, as long as it's settled at certain values, it's still considered as stable. Or maybe the response looks like this, it increase and then is having more than the input that you want, okay, but as long as it's actually settled at certain value, then it is a stable system. All right, so what does it mean by system is not stable? Let me just show you for the rest of this. Oops, hang on. Okay, so for RAM input, maybe for parabolic input, when I put that kind of input, a parabolic input, so I expect the system to be responding, maybe goes up and then goes down and die off. Okay, so then it's still stable. So if it's goes up and then goes down, but then it doesn't go immediately zero like I want, isn't it? Because the input is a impulse input like this, so I want it to become zero, isn't it? After sometimes it stopped, right? But let's say it goes up, but then it never stopped, it settled at certain value, that is still considered stable. All right, it's still considered stable. Why? Because it doesn't increase. Okay, it stopped at certain value. Similarly with sinusoidal, so if I have a sinusoidal signal, of course, I want the signal to behave the way my input is given to the system, isn't it? But maybe because the system have its own idea how to respond, so maybe it's responding that way. That is stable, all right? So when it responds this way, maybe bigger than your input, it's also stable. For sinusoidal, as long as the envelope is actually within a defined envelope, means the sinusoidal effect is within a certain envelope, then the system is still considered stable system. All right. When we say unstable system, what does it mean by unstable? Okay, unstable system is, let's say if I apply a step input to the system, it will behave this way. It will increase like this. That is unstable. All right, it will increase exponentially. Okay, exponential increment. Okay, all right, so it's actually it's not going to be stable. So also if I apply for example sinusoidal input or impulse input, like let's say sinusoidal input, this is my input, let's say, okay, so how does the system respond? Maybe it will respond like this and then become bigger and bigger and bigger, and the envelope is actually becoming bigger. Okay, so this is unstable system. All right, so this is the envelope of the system is becoming bigger. This is more like a resonant frequency. Okay, it's actually becoming bigger and bigger with time. Okay, so system is said unstable when it's increasing in its response when given a standard input to the system. This is what it means by a stable system. But if you look into the mathematics of the system, okay, if I have a transfer function, let's say the transfer function gs just now is equals to, let's say it's a first order system of, let's say, 10 over s plus 5. Okay, so this is a stable. Is this a stable system? All right, so if you want to know if the input is stable or not, you have to apply input to the system. All right. So if I write in terms of transfer function is actually equivalent to output over input, isn't it? If you remember equation of transfer function, y is equals to transfer function multiplied by input, right? Output y is equals to transfer function multiplied by input. If you remember this, all right. So then when we have a transfer function, it is actually output y is equals to 10 over s plus 5 multiplied by u. So when you want to test the system if it's stable or not, you need to apply input to the system. Okay, you need to supply input to the system. Like for example, I want to check if the vibration of the system is stable. I will actually knock the structure, okay, and let it vibrate and then see after some time does it settle down or not. If it settled down to a certain value, means the system is stable. As simple as that. So we need to apply input. Let's say I apply input of us is equals to, let's say it is a step input 1 over s. Okay, so this is step input in Laplace domain, all right? S is in Laplace domain. So if I apply step input to this system, what happens is that mathematically ys is going to be equal to 10 over s plus 5 multiplied by 1 over s, isn't it? Okay, so when we want to solve this equation in mathematics, so this actually need to be, what do we need to do? We need to do partial fractions. Okay, if you remember partial fraction, do you remember partial fraction? I hope so. You're a master student, you must remember. Okay, you need to do partial fraction and then you need to know inverse Laplace. Okay, so in order for you to find the time response of the system. So I'll do that one example. Ys is equals to, now if I do partial fraction, I'll just say that this is equivalent to a over s, oops, plus b over s plus 5. Okay, I just, because I want the denominator to be the same later on, what do? Is that I will just cross multiply. Oops, 5, I forgot the is gone. Okay, so I will do cross multiplication. I will have a multiplied by s plus 5 plus bs. The whole thing is divided by s plus s multiplied by s plus 5. Now I can say that this equation is equivalent, isn't it? Okay, I can say it is equivalent, okay, because equivalent to this equation 10 over s plus 5. All right, so since the denominator is already equivalent, this is partial fractions, all right, for those who don't remember. Okay, this is partial fractions, as simple as that. So what do I do is that I'm going to then find out what is the value of a and b. Okay, what is the value of a and b, and then since the value of the denominator is the same, so we might as well find out the value of the numerator. So if you look at the numerator, we have as plus 5a plus bs is equals to 10. All right, so from here you solve what is the value of a and b, isn't it? Okay, so if I compare the coefficient of a, compare the coefficient of s0, s to the power of 0, one side here we have 5a, the other side here, you know, this one is actually having it's multiplied by 1, so it means it's multiplied by s to the power of 0. S to the power of 0 is 1. Okay, so it means the coefficient of s is the power of s is 0. Okay, so this is equals to 10. Therefore, I can straight away get a is equals to 10 divided by 5, which is 2. Okay, so that's what I found. Right, then if I compare, this is comparing coefficient. So then if I compare the coefficient of s to the power of 1, what happens is that on the right side, I will have as plus bs. On the left side, I will have 0, isn't it? Because there's no value for s to the power of 1 on the other side of the equation, right? So look at this equation and then do the comparing of coefficients. Okay, so from that, I will then find out that a is equals to minus b, right? A is equals to minus b because we just look at the coefficient. Sorry, hang on. I forgot. When we compare the coefficient, you don't have to put the value of s there. You just look at the coefficient of it. Okay, so in this case, I have a plus b equals to 0. Okay, Then from there, I can just then find out that B is equals to minus of A. Okay, so since B is equals to minus of A, therefore I know B is equals to what? Minus 2. Okay, because A is 2. Right. So from that, this is partial fraction. So from that, I will substitute back the value of A and B into this equation here. Okay, so then I will have my response Y as is equals to 2 over S minus 2 over S plus 5. Is that all right? Okay, so it's A over S plus B over S, but B is minus 2. So we can have that minus 2 over S plus 5. Is that okay so far? So far, so good. Right. So when you want, after you've done your partial fractions, next, as I mentioned, the first one, you need to do partial fraction. Number 2, you need to do your inverse Laplace. So if I do inverse Laplace, guys, for this one, if I take inverse of ys, I will definitely get yt. So I want you to do is go back later on, find out what is Laplace transform so that you have to familiar yourself with this. So for 1 over s, if I take Laplace of that, inverse Laplace of that, 2 will still remain as 2, isn't it? Okay, so that is actually equivalent to this. This part is actually equivalent to 2 inverse Laplace of 1 over s, right? Okay, so Laplace transform of 1 over s is 1. So inverse of it will, in Laplace transform of 1 is 1 over s. Therefore, inverse Laplace of 1 over s is 1. So it's going to give me 1 multiplied by 2. So that's going to give me the value of 2. Okay, so this is the inverse Laplace of that will become 2. All right, and this side here, if I take the inverse Laplace of this side here, okay, so it is as if taking inverse Laplace of 2 inverse Laplace of 1 over s plus 5. In case of s plus 5, if you go and do your revision later on, have a look at Laplace transform of exponential of alpha t. If we have exponential of alpha t, if I take Laplace of that, it will give me 1 over s, if this is minus, then it's going to be giving me 1 over s plus alpha. All right. So Laplace transform, if you want to inverse it, the other way around. It's from here, you're going to get that. Okay. So this is similar to the Laplace transform of 1 over exponential of alpha t. Okay, so exponential of alpha t will give you that. So from there, you do your revision on this. Okay, I'm just gonna quickly show you the stability, so I don't have enough time to explain all about Laplace transform. Otherwise, we're gonna have a long class, one whole day of this class. Okay, so for this value, we're gonna have then that 2 if I take inverse Laplace of that, that will give me actually 2 exponential of minus 5t. Okay, when you go back later on, you're already back, you're in your home, I'm sure, but when you have your free time later on, go on and find out about this. All right, so in this case, the response yt is equals to 2 minus 2 exponential of minus 5t. Okay, so what is this? What we the question that I'm asking in the beginning is that, is the system stable or not? Right? We want to check the system stable or not. So when we want to check the system stable or not, we will give the value of t. We can start giving value of time. Okay, from time 0 until time equals to infinity, into this equation, into your response. So you apply, you give value of time when when y is equals to y0. What is the value? And then when y is equals to infinity, what is the value? All right. So this is how you do your checking of if system is stable or not. Okay. So then we plot the graph. You remember the input that we give just now is a step input. Okay, with the value of 1. We call it unity step input, isn't it? Oops. Okay, unity step input, where when we have us is equals to 1 over s, it means ut is equals to 1. Okay, unity step input. All right, so then I check the value of my yt. When I have my yt, if you look at that equation of yt, when t is equals to 0, yt is equals to what? Yt is equals to, put value of 0 at your exponential, negative exponential, okay? If you have t equals to 0, this is t here, isn't it? T equals to 0. You put value 0 here, okay? At your t here, you have an exponential of 0. Exponential of 0 is 1. Use your calculator, you find out the exponential of 0 is 1. So 1 multiplied by 2 is 2. 2 minus 2 is 0. So yt will give you value of 0 there. Okay? And then there's another value that you're going to put is when t is equals to infinity, what happened? Then when you have y infinity, that is going to give you t. When t is infinity, exponential of infinity is, what is exponential of infinity?
1.
Exponential of infinity is 1.
Infinity.
0, I think.
0.
0, 0 or infinity.
Exponential of infinity is 0. Then 0 multiplied by 2 is 0. So when you have 0 multiplied by 2 is 0, your output response yt will become 2, isn't it? Okay, so it means to say, let me just write this graph as smaller because it's going to take a lot of space. So it's 1. Hang on. The input response is 1. Sorry, excuse my drawing is very bad, isn't it? Okay, the input response is 1, all right, but the output response is 2, isn't it? And then the way it's responding is negative exponential. This is how negative exponentials look like. Okay, so you're gonna have, starting from 0, it will start to increase, suppress 1, and then it will stop at a value of 2. Okay, that's how your system yt responding. All right, so there's another important value because this is first order system. When you have t is equals to your time constant t. Time constant t is another story. But that is actually a value of 63.2%. I don't think I have time to explain all that because otherwise this class will take one whole day. Okay, but anyway, there's another value of time constant here. If I have value of time constant here, then that will give me a response of 63.2% of my state output. Okay, that is another value. That is time constant is just to show if the response is fast or slow. Okay, but when you plot your graph, you definitely will find out that, oh, there's an error here, isn't it? This is my error, isn't it? There's a huge error here, isn't it? Okay, that is your steady state error. Okay, so this is why you need a controller. What does it mean? Let's say this system is it is a system that I need the displacement. The response is the reference is a displacement. Let's say I want the displacement to be 1 centimeter or 1 meter for that matter. Okay, the displacement is 1 meter. But when I apply input to the system will give me double the displacement. It will be giving me 2. So the error is 100%, is equals to 1, isn't it? In this case, it's a huge error, isn't it? Okay, so in terms of temperature, for example, I want the furnace to give me a input, or I put a reference signal or a reference value to my furnace. The temperature is 100 degrees Celsius. So I want the oven to heat up at 100 degrees Celsius. But if this is the transfer function of my system, when I give that step input, what happens is that my system will respond with a 200 degrees Celsius, double the value of the reference that I give. So the error is really big. Okay, so that is why you need to design controller. Okay, you need to reduce that error. All right, and then another way of looking it is the time constant here. You want the response not only to reduce the error, but you have to respond very fast. You do not want to heat up your furnace and wait for one whole day for it is to respond to the temperature that you want, isn't it? You want to heat up your furnace, maybe within 5 minutes it is already heat up at 100 degrees Celsius, for example. Okay, so you want the system to first, the error is 0 because you don't want it to overheated. It will damage your products. Okay, if you put in a overheated furnace. 2, you want the response to be very fast. So this is the 2 objectives that I have explained in the previous class. Okay, so in this case, system is said to be stable. Why? Because you see the response settle at certain value. Okay, the response does not increase at that value. All right, how does it look like when the system is not stable? So if you look at the equation again, the reason why this equation is stable is because of that negative exponential. Okay, if I have my system, all right, with positive exponential, what happened? Okay, if the system is having positive 5t, exponential of positive 5t, this response will be a positive exponential.
Yes.
Negative exponential looks like that, but positive exponential, it goes up. Okay, so that only one value of positive becoming negative becoming positive will definitely make your system unstable. Is that okay?
Unstable, yes.
Yeah.
Yes.
All right, so it means to
We
say, if the value of my yt just now, if this is this part here, okay, this is the crucial part. If that value instead of positive, instead of negative, it's positive, then the system is gonna be unstable. All right, however, how does that, where can I get that value becoming positive? When can it be positive? The reason why it become positive is when this is negative, isn't it? Okay, this is all related, see? Okay, so if this is negative as, sorry, I don't have pointer, I forgot. If this is negative, if it's s minus 5, then your value of exponential will be exponential positive 5t. Then your system will become unstable. So actually, guys, system is stable or not, it can be looked at your actual transfer function only. You can look at the transfer function straight away. If that transfer function is having negative value there, your system definitely is going to give you a positive exponential, and then that positive exponential will give you a unstable system. All right, so let me just show you that now what happened. Okay, if that ys is so initially just now we have our system ys is 1 or maybe 10 over s plus 5, isn't it? Okay, so I multiply with u and then I will get the response, but actually the stability just by looking at this value, that value will determine your stability. All right, so that value is known as what is that value? What is that value? If you look at this equation just now, if I don't multiply with u, it's y over u, isn't it? This is closed loop equation, closed loop system equation, right? So that value is known as your characteristic equation. Okay, so if my y over u is equals to 10 over s minus 5, okay, if I apply step input to it, I will get y equals to 10 over s minus 5 multiplied by 1 over s, and then I do the Laplace transform and whatnot, then I will get a value of a response with what? Let's say I do the Laplace transform, I will get yt is equals to whatever value of a over s, sorry, ys, and then it's going to give me plus b, whatever value of b over s minus 5. Okay, no matter what is the value of your a and b, okay, it doesn't matter, your response will give you, oh sorry, let's have a look at the response in time domain. If I do Laplace transform of that, it will definitely give me a, because a will be multiplied by 1 over s, so 1 over s, we take the Laplace, the inverse Laplace, it's 1. Okay, b, Okay, it doesn't matter. It can be negative, it can be positive, it doesn't matter. All right, because it doesn't affect mass stability. What affect mass stability is, if you look at that, right, is exponential of positive 5t. That will make my system unstable. This is the major part. Okay, that will make my system unstable. So instead of going a negative exponential response, it's going to give me a positive exponential response. So the system is going to be unstable due to this part. All right. So that part, so means to say stability, you don't have to plot the response. You can tell the system is stable or not by looking at the characteristic equation and looking at the value of your what we call roots of your characteristic equation. So let me explain then what does it mean by roots of characteristic equation. It simply means this value s plus 5 just now. Let's go back to the value of s plus 5. So characteristic equation, I want to change the color. Characteristic okay, equation is actually the value of the denominator of your closed loop system equation. Okay, in bracket I can put denominator of closed loop system equation. So as long as you can write the closed loop of your system equation, the denominator part of it is characteristic equation. Okay, so characteristic equation, if I write, it is equals to, let's say I have a closed loop transfer function like this, okay? Let's say it's a closed loop over G over 1 plus GH, okay? Why? Why do I have this transfer function? It's a simple closed loop, or let me write down the simple closed loop transfer function. I want to, the moment I explain, there's a lot of things more to be explained. That's why I don't like to explain. Because the moment we write down the explanation, then at the back of my mind, and I remember, oh, there's a lot of other things need to be explained. That's why I hope you go and do some revision on control. Otherwise, it's going to be a very long day. Okay, so if I have a system looking like this, with a feed forward G, and then the feedback is H, with the negative feedback, input is U, output is Y. When I do, this is a closed loop system. When I do my closed loop transfer function, I will have Y over U is equals to G over 1 plus GH. Okay, this is why I call it closed loop system equation. All right, so characteristic equation simply means that value there. All right, so from that value, that the denominator of your closed loop transfer function, that will give you your characteristic equation. So it is equals to 1 plus GH equate with 0. All right, from characteristic equation in Laplace domain, you can obtain your roots of characteristic equation. Okay, what does it mean? Okay, when you obtain the roots of your characteristic equation, for example, let's say your G here is according to the previous value, let's say we have still G is 5 over, not 5, was 10, isn't it? Let's say G is 10 over S plus 5, and then let's say H is equals to 1. All right, so the feedback of your system is equals to 1. Okay, so what happened is that the roots of your characteristic equation is going to be what? It's going to be 1 plus G is 10 over S plus 5, multiplied by H is 1. This is equal with 0. Okay, it's going to give you S plus 5 plus S plus 5 plus 10, isn't it? Equals to 0. So that's going to give you S plus 15 equals to 0. That is your characteristic equation for this closed loop system. All right. So for closed loop system, this is your characteristic equation. So if you look at the roots, I want to talk about roots. Roots is equals to negative 15. So this is the roots of your characteristic equation. Okay, for this system. All right, so closed loop system equation giving you the roots. Okay, what does it mean by roots? Root is in S. Roots will actually give you poles and zero. If you look at your transfer function, closed loop transfer function, the denominator, if we equate with zero, it will give us what we call pole. Okay, so this is the relation between poles and zero. From a transfer function, if I have a transfer function gs, and I say that it is equals to 10 over s plus 5, this is not closed loop, okay, just a transfer function gs, right? So if I find if I put that in a closed loop system equation, means I give input u, I give that transfer function g here, okay, and then I give a feedback h, and then this is negative feedback. All right, then your closed loop system equation will become what we have in the beginning here, isn't it? Y, it will become not just gs, it's going to be y over u equals to gs over 1 plus gsh, isn't it? That will give me y over u equals to what we have here. So I have to do, Allah, I don't want to do this, but I have to do it now. So if I put, you can do the simplification, but if I put all of them together, 10 over s plus 5 over 1 plus 10 over s plus 5, okay, multiplied by 1, that will give me, okay, what? It's going to give me 10 over s plus 5 divided by s plus 5 plus 10, the whole
Plus 15 minus 15.
s plus 5. Yes, I just want to show. Okay, so if I cancel top and bottom, they're going to give me 10 over s plus 15. That's why we have our characteristic equation just now, s plus 15, isn't it? Okay, so this is the closed loop system equation. All right, and then from there, this is your characteristic equation. All right, so when you look at this system, do you know if the system is stable or not?
Yes.
Why do not assume s minus 15?
Yes, correct. Because if you look at the roots, okay, so I know because I've shown you in the beginning here, isn't it? So you straight away click into your head, okay, that will give you a negative exponential of negative 15. So yes, definitely it will give you a stable system. But if you look at the poles and zeros point of view, poles and zeros means when we have a transfer function, the numerator of our system will give us what we call zero. Okay, zero is actually the numerator of your closed loop transfer function. You equate with zero, that's the value of your zero. In this case, there's no zeros. Why? Because there's no roots. Okay, if I take 10, equate by 10, it will give me 0. So there's no roots, all right? There's no 0 in this case. No 0. Not that the value of 0 is 0. Now you're confused with the value and the name. The name is 0, okay, but the value is not there, all right? But if I look at the poles, it's the denominator of your equation. You equate with 0. That will give you, in this case, s is equals to minus 15. So this at minus 15 is known as poles. All right? In this case, there's no 0. Is that all right? Let's give you another example. Let's say a transfer function y over u is equals to 10 plus, maybe I give you one more example. S plus 1 over s plus 2, s plus 3. Okay? Do you know if this system is stable or not? Can you tell the system is stable or not? Now you're losing confidence, isn't it? Is this system stable or not?
Yes, stable.
How do you know it's stable?
Because it's positive.
Yeah, because it's positive. If you take Laplace transform maybe and do inverse Laplace like what we did, you're going to get maybe your y is equals to a over s plus 2 plus any b of s plus 3, right? Okay, so then you take Laplace inverse of this, you're going to get exponential of minus 2t, okay, plus b minus 3t. So you know, stable,
Yes.
okay, all right. But actually stability you can also tell in the form of your poles and zero, as I mentioned. So let's have a look at the poles and zero point of view. I normally write pz, okay, poles and zero. So in this case, if I take the numerator s equal with 0, I will have s equals to minus 1. This minus 1 is known as 0 of my system. The name is 0. The value is minus 1. Okay? And if I take denominator s equal with 0, this value will give me s equals to minus 2, s equals to minus 3. These are poles of my system. All right? So zeros and pole, we can plot the graph of zero and pole in what we call S-plane diagram. Because do you know S, guys? S is a Laplace transform, of course, is as a domain, but S is actually a value of a complex number. Okay, S is actually showing you it's a value of a complex number. So complex number, it have imaginary against and also real number, isn't it? Okay, so since S is equals to, it is a complex number, okay? If you know S is equals to what? S equals to minus J. Do you know? I don't want to talk about it. So it's going to be too much later on. Okay, just recall that S is a complex number. So if it's a complex number, means when I have S equals to minus 1 here, okay, it means that S is a complex number with real value only. Minus 1 is the real value only. There's no imaginary part. Okay, so if I plot in the graph, okay, of S-plane, that will give me minus value, minus 1, isn't it? Okay, so normally 0, we will actually plot and use the signal, the signal of circle for our 0. Okay, a circle. All right, so that is minus 1. That is my 0. For poles, we're going to use cross. So that is minus 2, minus 3. For poles, I'm going to cross. I'm going to use cross. So that is my poles. All right, so this one is 0. That's 0. Okay, and this one is poles. So that's my poles. Is that all right? So we can plot the graph, okay, for our poles and 0. Okay, in case of stability, the value of 0 doesn't play any roles. It doesn't matter. It will affect your response so that it is fast or slow, but it does not affect your stability. The one that affect your stability is your poles, all right? You know just now, isn't it? The value of that 2 and 3, if it's going to give you if it's a s plus 2, it's going to give you negative exponential, right? So it's a stable system. So with that positive s plus 2, it will give me a poles of minus 2. So when I have poles and as a negative real value, so my system is stable. If my poles lies on the positive value, okay, if any of my poles here, okay, then the system is unstable. Okay, so actually stability can also be defined by the location of your poles. So if your poles is a negative real, it lies on the stable region. If it's positive real, then it is unstable. Or if it's even a positive complex number, it is still unstable. So any poles on this side is actually unstable. Is that all right? Okay, so this is why we look at the value of poles in terms of it have to be more than 0, less than 0. It cannot be more than 0. It have to be 0 and lower. Okay, so if it's really exactly at 0, your poles is still stable. Okay, this part is called critically stable. So if it's s equals to 0, okay, for your poles, right, it is called critically stable. right? But anyway, any point at your positive real, it is unstable. Is that okay? Zero doesn't have any effect on your stability. Okay, so poles does have effect on your stability. So this is your S-plane. But you remember when we plot our graph, we don't plot on S-plane only, isn't it? So we plot in zero. Zero or the whole, isn't it? So for zero or the whole, okay, when you have z minus 1, isn't it, as your domain, similarly you can plot it, but it is within a unit circle. Okay, it's a within unit circle. Any point within that unit circle, of course it's all positive, this is a unit circle. All right, so any region inside the circle, your system is stable. Anything inside the circle is stable. So if you define your value of z is equals to 0.5, then it means to say your poles or your system is a stable, you're having a stable poles. So it's there, stable poles. All right. So if the value of z is outside the unit circle, z is equals to 1.2 for that matter. Okay, so this is unstable. Okay, is that right? So this is stable. Okay, so this is a concept of stability. It is the same actually. So either you look at time domain. For time domain, it must be what? For time domain, it must be negative exponential. Otherwise, it's unstable. All right. For Laplace domain, in Laplace form, it must be having poles with a negative real. Okay, for Laplace domain. Oops. And in fact, for your zero or the whole domain and z minus 1 domain, your poles must be within the unit circle. Otherwise, your system is unstable. This is how we define system is stable or not stable. Is that right?
Victor, just a question.
Yes.
Does that equal 0.5? How the system is stable and the value do not approach to 0?
Okay. Why give me tough questions? You need to look at the zero or the whole equation. Okay.
I think positive and negative 0.5.
Yeah, any value, if it's positive or negative, 0.5 is stable. But
Yes, I know this is equal the value in minus.
we put this in. Oops, sorry. We
But I
put this
about
in this.
Z.
Sorry.
Yes, I know this is equal any value by minus. But I ask about the Z.
Z, okay. I have to explain. It's a very long explanation actually. Maybe I have to have another hour of class on explaining how S can be changed to zero or the whole. All right, so the conversion. But the Z, just that it's actually the same when we have S equals to, I show you, isn't it? When we have time, in time domain, when we want the time to be infinity, okay, is the same by having S approaching 0 and Z approaching 1. So there's a big explanation on how we get to that. Okay, from time to S we use Laplace. Okay, so from that to that we use zero or the whole system, zero or the whole theory. So you need to study a little bit on that zero or the whole. How does that the same? Okay, how it become the same. So for zero, you need to study a little bit. Otherwise, I have to have another class. Maybe I will record another class showing the conversion from Laplace to zero or the whole. All right, so that is my another elective class actually, not this class. It's taking a longer time. I want to show you steady state response. Beside, maybe this one I can explain later, not today, because it will take a lot of my time. I'm thinking about it. Okay, but I want to show you the second objective, you remember when we go for our adaptive just now, the first objective is to make the system stable. The second objective is to make the system steady state error is 0, isn't it? Okay, so can I talk about the steady state error first? Okay, so if we have time, maybe we'll talk about that, how it convert to zero order whole in time in zero or domain. Okay, so let's talk about steady state error first. Okay, when we have a steady state error, if you remember the I don't know if you remember about this, when we have an input, let's say it's the same system. Okay, so that is easy for us to refer. Let's say I have the system of maybe simple system of 10 over s plus 5. Okay, that's the trans function. And then, or maybe not that, maybe initially, let's say initially without the closed loop. Okay, let's say the open loop of the system. This is open loop. When we have input applied to an open loop system like that, okay, the error is equals to what? Error is equals to the input minus the output. All right, the input minus the output. Let's say this trans function, instead of having value, let me just put that as simple as g first. Okay, so error in that sense, it's going to be equal to u minus y. In this case, what is y? Y is equals to u multiplied by g, isn't it? Okay, input multiplied by the transfer function. Okay, so if I put that y is equals to ug, then error is equals to u minus ug for open loop. Okay, this is open loop system. Therefore, my error will be equals to u1 minus g. Okay, so this is error. Normally, error, we use the denotation of ET. Okay, ET. So this is for open loop system. All right. So when we have a system, initially maybe we don't have a closed loop. We don't have sensor added to the system. We have the system, we apply input and we check the response of the system. Okay. So when we want to design controller, we need to close the loop. Why? Because when we design the controller, we want the system to know that the system is having error. Okay, then that is why we close the loop. Let me just show you a simple closed loop without controller. The same system, okay, this system, if I close the loop, maybe input is becoming the reference signal there. Okay, I don't have controller, so that's my G and that's my Y, and then I have my closed loop. Let put feedback there. Let put this is a sensor, means I find out what is the actual input to my system, and then I put into the reference. I'm so sorry, I have phone call. Let me just stop. Okay, so that's H. All right, so when we have this closed loop system, your error is this value here. Okay, the error is actually the comparison between your input and your actual output, right? But when you read your actual output, you're using sensors and you use all the instrumentation system and all. So maybe that is giving you another transfer function for your control closed loop system. All right. So the error is equals to E. Okay, now what is the value of error? So if I look at the error is equals to this is y going to h. So of course that value that added to the error is u minus yh, isn't it? Okay, u minus yh, right? Okay, and at the same time I know y is equals to eg, isn't it? E multiplied by g, isn't it? Okay. Okay, y u is equals to yh because this value is y multiplied by h. This is yh, right? Okay. So if I substitute the value of y into my equation of E, I will have E is equals to U minus EGH. Okay, if I substitute that y into this equation. Okay, so then if I collect the error together, so you see there's two part of error here, isn't it? So I will add them together, bring that EGH to the other side. I will have E1 plus GH equals to U. Okay. Then if I transfer that 1 plus GH into the other side of my equation back, okay, it's going to be divided by U, isn't it? Okay, 1 over 1 plus GH. So then I get my error equation. Error is equals to 1 over 1 plus GH multiplied by U. Okay, that is the equation for error in terms of closed loop system. All right, the first one that I gave you just now is the open loop system, right? This is closed loop system, but mind you, this is closed loop system without controller. All right, there's no controller into it. Okay, what do you think is going to happen? All right, when I have this kind of system, when you want to study the steady state error, okay, there's another one that you can use, another theorem that you can use. I think I mentioned this in the previous class. It's a final value theorem. Okay, so final value theorem says that, of course, this is just error equation. When you want to find steady state error, you must find the value of the signal at when time approaching infinity, or when s approaching 0, or when z approaching 1. Okay, so this is what you have in your previous class. I explained the previous class. Okay, so for final value theorem, your input, your steady state error, let me write steady state error. Or normally the denotation of steady state error is ESS. Okay, so this is the equation. Let me write at the bottom here. Okay, with E with subscript of SS, it's a steady state error. So final value theorem says when you want to find ESS, it is equivalent to limiting time into infinity, okay, of S multiplied by your ES. Okay, it must be S multiplied by your ES. What is ES? This is your ES. For open loop, this is your ET, but if you take Laplace transform of that, it will give your ES is equals to U 1 minus G with U in Laplace domain. Okay, so it's the same. All right, so for open loop, you have this as your ES. For closed loop, you have this as your ES. So that is the value that you're going to put there. Okay, so either open loop or closed loop, it depends on the value is depending if the system is open loop or closed loop system. All right, I'll give you a simple example. On maybe before that, this is in time domain. Sorry, I put in time domain. I put Laplace domain. Sorry about that. You never say anything, isn't it? You just allow me to look silly, isn't it? Time domain is not this. Sorry, it's completely wrong. It's ET, just like that. Limiting time into infinity. What? Okay, but when we want to talk about ESS, we'll change that into limiting S into, why? I make a lot of mistakes here. So sorry about that. So I made a lot of mistakes actually in my writing. So when you want to talk about Laplace, then yes, it's S approaching 0 and S multiplied by ES. Okay, so normally we will use this one it's easier for us to solve the steady state error in Laplace domain rather than in time domain. Okay, so for Laplace domain, ESS is equals to limiting S into 0 of S multiplied by ES, but that ES part is actually depending on your open loop or closed loop. So which one is you're going to use? So you use that. For open loop just now, your ES is equals to 1 minus G multiplied by U. For your closed loop, your ES just now is equals to 1 over 1 plus GH multiplied by U. Okay, so that's how you are going to decide. So let's have a look at one system. Let's go back to the first system that we have just now. U and the G is 10 over S plus 5. Okay, but this one you know already, the system is having error, isn't it? I want to show you system that you don't know. Let me give you different system. Let's say it's as simple as 1 over S plus 2 maybe. Simple one. So you know the system is stable, isn't it? S is the denominator S plus 2. It gives you a negative exponential. So you know system is stable. But this time around, we want to check system is having error or not. All right. So not stability, but error that we have. Okay. So let's say this is a system. So normally what you do is just you put your ESS is equals to limiting S into 0 of S multiplied by your ES. So in this case, your ES, because it's open loop, ES will be what? It will be 1 minus G multiplied by U. Okay, so you need to give input to the system. If you don't give input to the system, you do not know, the system will never produce error, isn't it, when it's static. So you need to apply some input to the system, then the system will start to respond. When the system is responding, then you get error of the system. So let's say I want to give input of a step input. For my input here, US is equals to 1 over S. It's a step input, okay? All right. So when I have that, what happened is that I put the value. So I put S multiplied by 1 minus G. My G is 1 over S plus 2, isn't it? Okay. Multiplied by my input. My input is 1 over S. Okay. Right. Then I look at this S here from my input and S here from my steady state equation. I can cancel that out, isn't it? Okay. I can cancel that out. And then don't forget, I need to limit the value of S into must be equals to 0. Right? So then is equivalent to, my handwriting is very bad, isn't it? It's supposed to be a straight line, okay? Don't forget that S is limiting S into 0. So then I just substitute the value of S into 0. Then I will get S is becoming 0 here. Okay? So what do we have? 1 over 2 is a half. So 1 minus 1 over 2 is half, isn't it? Okay, so this is 0.5. So I know for this open loop system, I apply a step input to the system just now in time domain. The value of my input is 1 and my system will respond negative exponential. How do I know it's negative exponential? Because this is a first order system. So it will actually respond in negative exponential. So negative exponential, but the value will settle down at 0.5 as my output. Why? How do I know it's 0.5? Because I know the error that it will give is 0.5. That is the error. Okay? So system is having steady state error of 0.5. This is how you calculate steady state error of a system. Actually, you can calculate in many different ways. This is one of them. Okay? Let's have a look what happened when the system is closed loop. All right? The same system. Let's have a look at the same system. Now that I know the system is giving me error, I don't like it because it's no good. What does it mean by this error? Maybe I want the system to give me a temperature of my furnace just now temperature of 100 degrees Celsius. Then when I switch on the furnace, after a few minutes, it will start to respond, and then it will stop responding. Then I know it is at steady state, and then the value, the final value it give me is 50 degrees Celsius. So it's no good, isn't it? I want the furnace to be 100 degrees Celsius. I want to bake a cake, isn't it? But what happened is it's giving me half of the value I want. So my cake is not going to be a cake. It's going to give me I don't know, a very flat one, okay? Very hard and flat cakes. All right, so it's not because I'm not a good cook, it's because of the system error, steady state error of my oven. All right, so this is how it means by steady state error. Now, I know the system is no good. What I'm going to do is I'm going to close loop the system, okay? So maybe that will improve the system. So let's have a look when I close the loop, okay? So if I close the loop of my system, let's have the same system, 1 over S plus 2 just now, isn't it? Okay, without controller. Okay, I don't want to put controller. Maybe H is equals to 1. So just to make my life easy, okay, H equals to 1. So H is equals to 1. All right, in this case. So what is the transfer function now? Is become different than before. Okay, before is just S plus 2. Now the transfer function is slightly different, right? Okay, but I don't want to talk about the transfer function. I just want to talk about my error equation. So this is G. There's no H here. I put a one loop like that. H is equals to 1. If it doesn't have any transfer function, it means to say the value of that transfer function is 1. Okay. Right. So go back to the steady state error equation. Now that you think you close the loop, maybe the system perform better, isn't it? Do you think so? What do you think? Do you think the error will be reduced or not?
Should be better.
It should be better. Okay, Saleh, do you think so? Khaled, do you think it's better?
Yeah, I said that.
You said that better. Okay, great. How about Abbas? Do you think the system gonna be better?
If H equal 1,
Yeah. Do you think the closed loop system, the error will be better?
I think error will be better.
Why you all think? You don't think, okay? You must calculate.
Because I have to write in my hand.
Are you writing? It's okay. I'll give you this note. Don't worry.
Yes.
Okay. So if I have ESS, if you remember just now, limiting S into 0, isn't it? Of S, ES. And then now the ES is no longer similar as before. Now the ES is for closed loop system. So I have to change the equation for my ES, right? So it's going to be limiting S into 0 of S multiplied by my ES now has become 1 over 1 plus GH multiplied by U, isn't it? From my previous derivation. Okay, so let's say input U, I still give the same input, a step input for my U. Okay, so I'm just going to keep similar input to be fair for the system. All right, so it's a step input with value of unity, step input. All right, so what happened is that this equation will become limiting S into 0 of S 1 over 1 plus G. My G is 1 over S plus 2. My H is equals to 1. So this is going to be 1 over S plus 2 multiplied by 1, right? Multiplied by input 1 over S. Okay, the input is 1 over S because it's a step input. All right, straight away I know the input can be cancelled, isn't it? With this equation here, isn't it? This S can be cancelled with the S, all right? Okay, so then I just focus on the remaining equations. So I have 1 over 1 plus 1 over S plus 2. And the S is equals to 0. So if I put S equals to 0, what do I get, guys?
1 above 1 plus
1 plus 1.
No 1 plus 1. There's 2 here.
1 over half.
1 above 1 plus half.
Plus half.
1 plus half.
That's 1 plus half, yeah.
1 plus half is 3 over
3 plus.
0.8.
3 over 2, isn't it? Is it 3 over 2? 3 over 2. Right? Then what do we get?
2 over 3.
This is error, right? We are talking about error. Is it better?
Actually, no.
No.
Actually, no.
It's not better, isn't it? This is what I'm trying to show you. It's 0.6667. Okay? So, oh my God, the error increased. It's supposed to be better. Why is it increased? This is what happened when you don't design system with controller. When you close loop of any system, first order system, when it's already having error, you close the loop, the system will give you bigger error. That is why when you close loop of the system, you need immediately design controller. All right, this is why it's important to design controller. All right, so yes, the error is not less than before. Before we have a half, isn't it? Let's write the one with open loop. Open loop is we have this is open loop system just now. This is 0.5, isn't it? Before we have the error is 0.5. Now you have even worse. Okay, even worse.
Yeah.
Your closed loop system, your error is how much?
0.66.
Yeah, it's more than before. And the response is at 0.333, I think. 1 over 3. Okay, so yeah, the system is giving you more error if you close the loop. So simply closing the loop will not help you on in terms of error of the system. You need to design a simple controller for that matter. Okay, so let's say if I design a very simple controller, very simple controller. Okay, instead of having input directly to the system, let's say I have one controller here, a P controller. Okay, from PID, maybe a P controller, just put GC there, a controller. Okay, then this is my trans function just now, S plus 2. Okay, then this is my signal, negative feedback of the system. So I have a simple controller there, isn't it? Okay, so let's say that simple controller, I just put a value of maybe 2. Okay, or let me write somewhere. Otherwise you forget later on. Put controller GC here. Okay, let me just write somewhere. This is a transfer function of system GS. Now, your total G, your overall G is becoming GC multiplied by GS. Okay, so it's no longer just one transfer function on the feed forward. H is still the same. Let's say H is still 1. Still the same, doesn't have any changes. All right, but now I have a controller there. All right. Okay, so I use the transfer function. Let's say the controller is GC. I call it GC. Okay, so what happened to my closed loop system equation? My steady state error will become limiting S into 0 of S multiplied by ES. But that ES have changes a little bit, not much, okay, because that changes is becoming my G becoming this value. Therefore, my ES is becoming 1 over 1 plus, instead of just GH, it becoming GSGCH. Okay, with the controller, because that G part, you have two part now. You have G and GC because it's in parallel. I just put a parallel transfer function. So the total transfer function is just a multiplication of it. Okay. So your ESS, if I put value, let's say GC is equals to 2. What if I have GC, GC, the controller, equals to just a value of a constant 2. Okay, what happened? So my error will be limiting s into 0 of s multiplied by 1 over 1 plus your gs is 1 over s plus 2. Your gc is 2. Right? Or I can just multiply that. It become 2 over s plus 2. All right, multiply by your input. Don't forget you have a step input, and then straight away step input is actually cancelled with that s there. All right, okay, so what happened to your error, guys? Have a look at it. If I put s equals to 0 into that bracket, okay, what happened is you have 2 over 2, isn't it? 2 over 2 is 1. 1 plus 1 is 2. 1
That
over
means
2 is a half.
full half.
So it's same.
Yep, it becomes 0.5. It's better than without controller, isn't it?
Yeah.
It's better, certainly better.
It's certainly better than without controller. What if I have a bigger controller? Let's say my GC is not 2, it's 20. Do you think it's going to be better?
Yes, better.
It's much better, isn't it? If I have GC is equals to 20, then my system will be ESS equals to limiting. Let me just take that. No. So it's becoming S multiplied by 1 over 1 plus. So in this bracket, instead of 2 over S plus 2, it's now 20 over S plus 2, isn't it? Okay.
Yeah.
20 over S plus 2 multiplied by S, and then S equals to 0. So yeah, we cancel that part from that. Okay, and then I substitute S0 into the equation. I'll have 20 over 2. 20 over 2 is 10.
Yeah.
10
Plus 1,
is
11. So I will get 0.09.
Yeah, 0.09. Okay, that's great. So it give me error
Almost 0.
0. Not 0.09, it's 0.09, isn't it?
Yeah.
0.19? 1 over 11. What is 1 over 11? No, 1 over 11.
Yeah.
10,
0.09.
0.09, 0.09, isn't it?
Yeah.
Yes.
Let me just check. Yeah, 0.09. Okay, so it's actually 1 over 11. So it's actually really small now, isn't it? Very small. It's very good, right?
Very good.
Error is becoming 0. Okay, what happened, guys? In this case, okay, there are two things. We look at two things just now, isn't it? Stability and steady state error. For this system, a simple system here, even if I put my controller is equals to 1000, the system will be stable. Okay, the system will be stable. All right, even if it's 1000. I know if I put my controller GC equals to 1000, of course my error will become 0.00001 or maybe, isn't it? So it's becoming smaller and smaller error. Okay. However, some other system, you cannot simply increase the value of your controller into a bigger value because it will affect the stability of the system. In this case, in this particular example, it's okay. It doesn't affect the stability of the system. All right. But in a different system, it might affect the stability of a system. Right? So that is why when you want to increase the value of your controller, you must do together with the stability, because you want to increase the value of the controller to reduce the error, and the objective is also to make sure the system is still stable. All right? So that is why for the adaptive control, we put this together. We put the objective together. All right? In this case, for this particular example, it's all right. As long as I increase the error, increase the controller value, the system will still become a stable system. But in other different system, it might not be the same story. It might be completely different. Okay, I can give you other example than this, but that will take a lot of my time explaining that, okay, because this is just another part, or not, this is not part of adaptive control. It's just to show you why do we have this kind of objective for our adaptive control. Okay, is that all right?
Right.
Okay, so in fact, guys, so let's have a look at this controller. What if I change this, when I put GC equals to 2, this is a P controller, you know, it's a PID controller with a value of KP equals to 2, isn't it? This is P controller. Okay, we call it P controller. I will talk about PID later on in our class. This is also when I have GC equals to 20, this is also P controller. Controller PID. Okay, what if that instead of GC equals to 2, I put it GC equals to 1 over S. This is I controller from PID, okay? What do you think happened when I put GC equals to 1 over S? My error equation, steady state error will be the same as before, limiting S into 0 of S multiplied by my ES, okay? And then that ES will become different, isn't it? The value of ES is 1 over 1 plus GC multiplied by GH. So GC is already 1 over S. Then I have GH is 1 over S plus 2, isn't it?
Yeah.
Okay, GC multiplied by H. Let's say H is still 1. Then don't forget my input, 1 over S, right? So in this case, the input can still be cancelled out with that value there. Okay, the remaining, let's have a look at this part. The remaining, I have 1 over 1 plus 1 over S plus 2, isn't it? Okay, and then I have to limit all the S into 0. Okay, so what do we have? When I have S0, I have S plus 2 become 2. Okay, 2 multiplied by 0 is, what is 2 multiplied by 0? 0. 1 over 0
I will get
is,
1.
1 over 0 is infinity. Infinity plus 1 is
Infinity.
is infinity. 1 over infinity is
0.
0.
very good. It's 0. You see, with a simple integral controller, cancel the system, it automatically become 0. Why didn't I do this in the beginning? Why do I make myself all the trouble to use P control? I can just straight away use I control, isn't it? What is the reason? Anybody knows?
What's
No,
the question?
I controller is very good, isn't it? I controller
Very good, very good,
will give me 0, right? Error?
Yes, stable.
Okay. Unfortunately, I controller will make your system slower. That's the problem. So yeah, everything in control is related. So when we change the controller, P controller, for example, we increase the value of P controller just now into a very big value, it will affect the stability of the system. Not for this system, but for other system, it will affect the stability. But then we change into I controller. So when I use I controller, what happens is that it's very good with value ki over s, with even ki equals to 1 over s, then I will cancel the error, immediately becomes 0. Very good. Okay, but then what happens is that it will affect my system response. It will make my system slower with I controller. So instead of having, of course, the error becomes 0, okay, but the system will be like that. Do you want this? So that's how your system responding. Do you like this one?
Definitely not.
So it means to say How slow? It depends on your transfer function. It can be slower for different different system, but it definitely slowing down your system response. The error, yes, 0. Definitely no error with integral controller for this particular system, first order system. But the system becomes slower. Slower means maybe if I want to use my oven just now to bake a cake, I have to wait 1 hour before I put my cake. I might as well go to restaurant, go to Secret Recipe and buy.
I will still angry.
Yeah, no need to bake a cake to wait for 1 hour, isn't it?
So we have error better than we have 0.
It's a better because we have 0, but the response is very slow. So maybe it will cost us more. The time will be another issues. So in this case, you have to compromise the controller. You have to design the controller so that it solve this kind of problem. One, make sure the system is stable. Two, make sure the error is eliminated or becoming as small as possible. Number three, make sure the response is fast. In this first order system, it's just the response of the system. If you have second order system, third order system, the transient, there's a lot more. In this case, first order, so the transient part is just whether it's a fast response or slow response. But for second order and higher order, you have to think about the overshoot, you have to think about the sinusoidal part, you have to think about the rise time. So there's a lot of effect on the transient part that you have to handle within when you design a controller. So designing controller is not as simple as that. Okay, so what I have shown you is the reason why our objective of designing controller. But of course, this is a very simple system because the transfer function doesn't change, isn't it? Okay, so the transfer function remain the same. But our problem in adaptive control is even worse, isn't it? Why? Because you design the controller, at the same time, your transfer function changes. So your controller also need to be changing. Okay, that is why I shown you. Let me go back to the slide. That is why even for this type of controller, we design the controller so that it is as a function of our system. Okay, so it is a part of our system. So if you look at the closed loop poles here, all right, so oops. If you look at the closed loop poles, we just want to make sure the closed loop poles is stable. So we want that Z is equals to a certain value within 1. Let me erase all this. Okay. So we want the Z to be a certain value of our our poles here. T1 must be the design rules. T1, you decide the T1 just now must be, if it in Laplace transform, it must be a negative value of poles, isn't it? Real, negative real for your poles. But it is, if it's in a 0 or the whole, it must be less than 1. Okay, it can be 0.1 until maybe even less than that. It doesn't matter as long as it is less than 1. Okay, maybe 0.5, maybe 0.7, anything, any value that is less than 1. Okay, later I will show you also how to convert from Laplace to 0 or the whole. Okay, I know you've been meaning to you've been waiting for that. Okay, but it will take me longer time to explain. Right, and then design rules number 2 here is that we want the response to have yt over rt equals to 1, means to say yt is equals to rt. When we have output equals to the reference, it means to say the system is having steady state error is 0. Okay, so this is why we have that design rules just now. Okay, so using these design rules, the 2 design rules, you have seen that we have actually designed it so that the system is having a stable system, and at the same time steady state error is 0. That's all for the first class last time. Okay. Hey, it's already 11. My God, I haven't shown you the second controller. Okay, so this is another controller, okay, that when we have the system but we have the disturbance with polynomial C at the output. I think we don't have time for that because it's already 11 o'clock. I will show you this in Thursday, okay, this control. But now you know that two system, stability and also steady state error of a system. All right, so but this one I will have to show you on Tuesday. Not Tuesday, Thursday. Okay. Any questions so far?
Okay. So far, so good.
Okay, good. Can you go through this equation and have a look at the design rules, because there's another part there. But now at least you know what does it mean by characteristic equation, what does it mean by stable system and unstable system, what does it mean by error of the system. Okay, so and how to check the system error. So let's conclude for for today class. So let's stop here, and then I will go and explain the pole assignment regulator. Either I send you a recorded video or I will have an online class like this on Thursday. Okay, thank you so much.
And please, Prof, don't forget the last lecture, because of the last lecture.
I will give you today.
And about the test one, Prof, test one, the solution will be used MATLAB or manual, about the parameters.
Sorry, the parameter?
Yeah, the test one.
Test one. Oh, okay.
Yeah.
Test one, you're not using MATLAB. You have to use manual calculations.
Okay.
Okay. So yeah, you're gonna use manual calculations, and then you're gonna calculate the error and all. Yeah, you don't use MATLAB. You can use your calculator, of course.
Okay. Because
Alright.
the MATLAB takes a lot of time.
MATLAB taking a lot of time. It's actually quite the opposite. MATLAB is faster. MATLAB is faster.
Excuse me, bro.
Prof, when that
How
test
many
one?
listeners will be included in the test one? Because I entered lately in the class.
Okay, next week we don't have class on the whole week because it's a break, isn't it? It's a semester break. Okay, I'm quite surprised it's a semester break. The time really fast, really fly, isn't it? Very fast, isn't it? It's a semester break, so I need to have the test made. Actually, I need to have the test before the semester break. But since we have not having a lot of classes, so it's okay. We can have the test after the semester break. So maybe on Tuesday or Thursday. Okay, the topic that I will cover is least squared and generalized least squared. Okay, these two things. Okay, least squared and generalized least squared, and the first this adaptive control. The simple adaptive control with pole assignment. All right, the simple pole assignment adaptive control. Is that right? So this one. So there will be three questions. One is your least squared. One is generalized least squared. The other one is the adaptive control with pole assignment, but a simple one, not with polynomial C and all. Okay?
Okay, thank you, bro.
All right, great. Any other questions?
We have exam instrumentation after break semester, so we can change it another time.
When
Or
is your instrumentation test?
on 14th.
14 December.